Howdy. I was just reading this article and I noticed some, even funny things. The Observer, Physics, interview. Nobel Prize winner Giorgio Parisi. There is a lack of trust in science. We need to show how it's done. The Italian physicist puts the friendly trick theory of complex systems in terms of birds and bus rides, as his new book aims to make his branch of science accessible to all. Yeah. An interesting door he has in his living room. Anyway, maybe it's not his living room. The multi prize winning theoretical physicist. That's already something, a theoretical physicist. Giorgio Parisi was born in Rome in 1948. He studied physics at the Sapienza University in the city and is now professor of quantum theories there, a researcher of broad interests. Parisi is perhaps best known for his work on spin glasses, or disordered magnetic states contributing to the theory of complex systems. I have to admit I don't really know what the theory of complex systems is, but maybe I will once learn about it. Anyway, for this work, together with Klaus Hasselmann and Syukuro Manabe, he won the Nobel Prize in Physics in 2021, his first popular science book, In the Flight of Starlings, The Wonder of Complex Systems, which charts some of the highlights of his life's work and makes a passionate case for the value of science, is published on 11th July. How did you get interested in physics? As a young child, I was interested in numbers. My mother told me I learned to read the numbers aged 3. On the street, we'd be waiting for a tram, and I'd say, "Here comes the number 6." When it was time to go to university, I pondered if I should do physics or math. But in the end, I went for physics. Maybe because there were more popular books on physics than mathematics, which is so abstract that it's difficult to describe. What prompted you to write the book? The original idea was to describe how science is done. There's a growing lack of trust in science. Yeah, like if you really start to read about many things, geology, for example, or cosmology, or whatsoever, you will figure out that they actually don't know, and very often they just tell it you straight at the beginning of whatever paper. Now let's take the example of water, which I have been talking about recently. But anyway, there's a growing lack of trust in science, with people denying COVID, or the need for vaccinations, or climate change. So we have to assume that he has this general notion of how things are and work. But anyway, in order to address this, it is very important to show how scientists do their work. Your work can be fiendishly complex. Was it a challenge to write a book about in an accessible way? Yes, it was. For me, it's very important to use metamorphical language. Sometimes in popular science books, people write formulae. That would save a lot of time, but I would lose a lot of people because a formula that seems easy for me to read is harder for other people. So, trying to describe some complex and sophisticated physics problem without formula takes real effort. Yeah. You know, if you watch outside of your window, if you go to the forest, if you go to the river, if you go to the mountains, which are all very complex systems and stuff like that. There is no numbers. You won't find any 3 in the forest. But anyway, you begin with writing about your study of starling murmurations, which seems an unusual subject for a physicist to tackle. Why was it worth exploring? We wanted to see if there were rules of interaction between starlings that account for their collective movements. This connected to attempts in physics to understand the behavior of systems composed of a large number of interacting components. In Rome in the winter, every evening, we see starlings flocking above the trees, forming these amazing patterns. Yeah, they don't make numbers. One of the problems was to understand the three-dimensional shape of the flock, which is impossible to capture from a single viewpoint. It was clear to us that this had to be done by physicists because of the huge amount of data that had to be analyzed. Yeah, what an attitude. Anyway, the experiment sounds like a huge amount of work. It took a lot of time and effort to create a 3D image. We positioned 2 cameras 25 meters apart. 2 cameras. On the roof of the Palazzo Massimo in Rome to track each individual as they moved. There were thousands of birds and we had to reconstruct the 3D position of each one. When you have 2 simultaneous images of a flock seen from a different angle, it's not easy to match the bird in the first image with the same bird in the second. This was one of the major difficulties. What were some of your findings? When the flock was turning, yeah, actually, I really have to say that. We positioned 2 cameras 25 meters apart. If anyone would have asked me, I would have positioned them like really further apart from each other, maybe 250 meters or whatsoever, because those flocks are really big and they move like, it's a big thing to watch. So 25 meters is probably too much. And if you think about like there's 2 cameras on the roof of one building and those birds flying there all over the place, probably you should see it also from the other side in order to get a 3D image. But this is just what I think. When the flock was turning, the impression that one has is that they are turning as a flock. But the reality is that some birds start to turn in advance and the others follow. We were able to get the acceleration of each bird and to see that some birds start to accelerate or turn in one direction and other birds follow, and that this decision was propagating inside the flock. We also found that the flocks are flat like pancakes rather than spherical. And that's one reason why they can change shape so quickly. The flatter the object, the more it gives you an impression of change when it changes orientation. Yeah, they are connected. Birds, they navigate with their magnetic senses. So probably when they fly around, they are very closely connected to each other. They fly in each other's auras and, they are one. Like somehow, if you watch people in the city, they're like just sometimes they're moving like there would be one bigger individual moving there. But since they are totally unaware of what's going on, they probably don't notice. But the birds, they are probably to some degree aware of what they're doing because it's their thing. Oh, you also found that the flock was denser at the edges than in the center. This was completely unexpected. It's a bit like what happens on crowded buses. where frequently the crush is greatest near the doors where passengers who have just got to accumulate, together with those who are about to get off and others still who want to continue their journey. You are best known for your work on spin glasses. What are spin glasses, first of all? There are hundreds of materials called spin glasses, but the typical ones are an alloy of gold with a small amount of iron. For physicists, spin means something magnetic. Yeah, it depends on the polarity. Like weather system, high pressure system will always spin counterclockwise, I think, and a low pressure system will spin the other way. And if you go to the other side of the hemisphere, it will be the opposite, because we have a north and a south pole, which is also polarity. So it will be the opposite of the polarity. But anyway, for physicists, spin means something magnetic because magnetism is related to spin. Yeah. To the fact that electrons turn around and work like small magnets. At high temperatures, they behave like normal magnetic systems, but when the temperature falls below a certain value, they appear to behave like glass. In that the magnetic changes get slower and it seems as if the system never reaches equilibrium. What's the equilibrium? They stop to spin, cease to exist, or what? Yeah, now that's the funny thing which triggered me to make a video about this. I won't read more than that. You can read this stuff if you want to. But now it comes something really funny. What are some of the real world applications of this work? Real world applications of this work. One direct descendant is artificial intelligence. Really? Real world application? And you talk about artificial intelligence? I don't know. Like, he's a theoretical physicist or whatsoever, like, thinking about imaginary stuff, I think, most likely. Like, if he talks about climate change, how he probably does, according to the other notions he's living in. What are some of the real world applications of this work? One direct descendant is artificial intelligence. You must be kidding. Like, Nobel Prize winner talks this kind of things? Real world application. Artificial intelligence. Yeah, it's maybe not the real world, dude. But anyway, this is just what I think. Thanks. Bye.